So let's see how we can adapt the proximal gradient method we use for Lasso to solve the elastic net problem. Well, actually, it's going to turn out to be pretty straightforward. We simply redefine our smooth function as this. The non-differentiable part stays the same, of course, it's just this one norm. And now rather than just lambda, we have a lambda 1 here and a lambda 2 here, which is absorbed into this smooth part. So the proximal step becomes the following. We apply the same proximal map, soft thresholding operator, with some parameter alpha. And now our function is this. So all we've done here is we've changed lambda to lambda 1, just relabeled it. And we apply it to this update here, this gradient descent update. But now this update relates to this smooth function g here, right? Before we only had this, now we're adding this ridge component to it. So we take the gradient of this and evaluate it at theta I. And that's just going to be, well, this is the dot product of this with itself. So we're going to get 2. That will cancel the half. And we're just going to get y minus phi theta, right? Or the other way around, minus that plus that. And it's evaluated at I, theta I. So we get this. And from this part, we're just going to get plus lambda 2. The 2 will cancel the half, and then we'll get theta, and we evaluate that theta I. So we'll get this. And that's what we have. Oh, sorry. We have here. Let me rewrite this. We're going to have phi transpose theta I minus y plus lambda 2 theta I, which is what we have here. Right? And that's multiplied by this alpha here. And we can rearrange this so that we have 1 minus alpha times lambda 2 times theta I minus alpha phi transpose times this. And so we pass this whole thing, which is the gradient descent update, now for this smooth function, through our proximal map that we developed for the one norm times some arbitrary constant, in this case lambda 1. And so we have the following algorithm. The first step involves starting at theta I, performing a gradient descent update to get, let's say, a half step theta prime equal to this. Then we simply pass that through our soft thresholding operator with some parameter alpha I, and with our lambda now equal to lambda 1. And so we have this result here. And that's it. So we don't need to do anything new. We already developed the components that we required. The only thing that we needed to do was calculate a new gradient, right? And from that, we get a new gradient descent update, which is this. And then we just do exactly the same as before. We just pass this through the soft thresholding operator. We're going to look at an example of Ridge versus Lasso and Elastic Net. Before I start, I just want to point out that the code, the Python code for this example, is included in the description to this video. So if you look in the description, you will find the Python code and you can play around with it. So once you've understood the example, I will explain it. You can mess around with some of the variables in there to see how these different methods here, the 3 different methods, compare to each other. So let's have a look at an example in which we compare Ridge with Lasso and Elastic Net. Now, what I'm going to do here is create a totally artificial data set, because the idea of this example is, as I say, comparing these 3 methods. And so we need a certain structure to the data set. Now, what we're going to assume is the following, that we have data y, I, and xi pairs from I equals 1 up to n. Now, these yi are scalars. The xi are vectors. So a general x looks like this, x1 up to xp. There are p of them. Right? Now, the true relationship that we're going to have is that the expected value of a random y given x, given, so this is a realization of a random vector x, and this is a realization of a random variable y. So the expected value of y given x is actually just x1. Right? It's the random variable x1 of which this is a realization. And we have another p minus 1 of these. Right? And none of those are going to influence the output y. We have designed our data, our synthetic data, to basically have only have a dependence on the first one of these, the x1. So this is the true relationship, but we don't know that. The point is, all we have is this, where these are vectors, right? And they have p components, only the first of which actually influences the outputs. So this is all we have from I equals 1 up to n. This is our data set, and we have to propose a model, right? Not knowing that what we've really done is generated the data as follows. It's equal to, the outputs are equal to the first of these features or inputs plus some random noise. So clearly, only the first of these actually influences y. So the expected value of y, given our vector x, which is a vector of these random variables, x1, it's a random vector, the expected value of y, given this random vector, is actually just x1, right? Because the expected value of this is going to be 0. So by the linearity of expectation, this is going to be the expected value of y will be the expected value of x1 plus the expected value of epsilon, but that is just 0. Right? We are generating this data as x1 plus some noise with mean 0 and variance sigma squared, and it's normally distributed. So the expected value of y given x is just x1. As I say, this is a synthetic data set, and we are going to pretend that we don't know this. We've generated this data set because we want to see how Lasso and Ridge and Elastic Net perform in this case. But as far as we're concerned, this is all we have, where these are vectors, the first component of which are realizations of this x1. The rest are realizations of the rest of these. Okay, so to reiterate, we're going to generate synthetic data, which is the sum of some random scalar input, x1, let's call it, plus some Gaussian or normal noise with mean 0 and variance sigma squared. So we're going to propose this linear regression model here. We're going to propose a linear regression model in which we have linearity, of course, we have to, by definition, linearity in our parameters theta, but also now linearity in our features or inputs x1 to xp. So this is an example actually of classical linear regression. So our predictors here, the psi I of x, are just xi from I equals 1 up to p. Right? So the general, if you remember the general linear regression model, is f theta of x is equal to the sum from I equals 1 up to p of psi I of x times theta I. So in this case, what we've got is this is just xi. So it's theta I times xi. Precisely what we have here. We have a sum of theta I xi. Now, to make things interesting, we're going to give the data a particular structure. When I say interesting, I mean interesting in the sense that we want to compare Ridge with Lasso and see what are the benefits of Lasso and Elastic Net compared to Ridge. So what is that structure that we're going to give this example? The components of X are going to be as follows. So the first component of X, as we know, as I've already defined, is going to be X1. This is what we can call our true signal feature. It's the one that influences the output, and it's the only one that influences the output because we generated our data like this, right? It's influenced only by X1, and we add to that some random noise, so we have this relationship here. So this is what we really want to extract. We want a prediction rule. Basically, we want a prediction rule f theta of x that's going to end up being just x1. That's what we want, right? So this is the sum of theta I xi from I equals 1 up to p. So basically, and we can write this as theta transpose, the vector of these thetas, x, right? So what we want for this theta, this vector theta, the true vector looks like this: 1, 0, they're all 0, right? Except the first one. Because then that would give simply this, all of these would be 0 except the first one, theta 1. That would just become theta 1, x1. And theta 1 is just 1, so we'd get x1. Theta 1 is 1. So this is the true theta. Theta 1, theta 2, up to theta p. So that's the first thing, which I've already explained. The second is that we're going to make the second feature highly correlated with the first feature. So this is going to lead to collinearity, right? Which I've already gone through and explained. And I also explained in great detail why this leads to instability. What we have in that case, let me remind you, is that our matrix phi transpose phi doesn't have an inverse. This doesn't exist. So solutions are not unique. We could, solutions can still be extracted, but they're not unique, or certainly not necessarily unique. And this creates a problem, which I'm going to discuss in a second. Okay, so the true signal feature is just x1. We're going to make x2 highly correlated with x1, so we can see, in this case, how these three methods perform: Ridge, Lasso, and Elastic Net. The rest of them, x3 to xp, are just going to be noise variables. In other words, we're just going to select random numbers, right? And because the data is generated like this, those x3 to xp don't appear in here. They will have absolutely no bearing on the values of y. We're just going to select random numbers, and they do not appear at all in the data generating process. This is why we want all of the theta I from theta 3 to theta p to be 0, right? Okay. Now I said before that, and I just mentioned it again, this phi transpose phi, if we want it to be invertible, we need this condition that the rank of phi is greater than p. So we need more data points than features p. Otherwise, as I explained earlier, the solutions are not generally going to be unique. In the case of Ridge, we also saw that this is not an issue. Even if phi transpose phi is not invertible, this new matrix is invertible because we changed the OLS solution from phi transpose phi inverse phi transpose y, the vector of our targets or outputs. We change it from that to the same thing, but we replace this with phi transpose phi plus lambda I, where lambda is the regularization or penalty parameter that we use, phi transpose y. So this is our ridge solution, theta ridge, right? And this is our OLS solution, theta OLS or linear regression solution. And this is always positive definite. It's always invertible. So we don't have a problem. We know this. So we're going to get, even if the number of features p is greater than n, when in theory we're going to have problems. We will have problems for if we do OLS and we have the solution I just wrote down, because the solutions will not be unique in general. But Ridge will select a unique solution. Okay, so that's Ridge. What about Lasso? Well, Lasso doesn't require that matrix. It doesn't use the inverse of phi transpose phi. So it doesn't require actually the design matrix to have full rank. So p greater than n is not necessarily a problem, but the solutions might not be unique, again, as in OLS. So what does this mean? Well, in and of itself, having a non-unique theta is not really an issue, because let's say that we have different thetas. Let's say we have theta 1. I don't want to confuse these thetas with the components of theta. Let's say we have theta 1, theta 2, up to theta k, right? So our solution is going to be our predictor f theta of x is going to be the sum of the components of this times the basis functions. So let me write it, since I've introduced this notation here. Let me write it like this: theta 1 transpose times the vector of our basis functions, right? So we can have theta 1. Let me write this as theta j, where we can use any of these. Now, what's going to happen if they all give the same result? So each of these is a solution, right? So they all give us the same result on the training set, the same predictions for the outputs in our training set. So each is equally valid. So we could use this one for prediction, theta 1, theta 2, all the way up to theta k. So does it really matter that we don't have a unique solution? Well, if prediction is all we're interested in, no, it doesn't matter. But here's the issue. From the point of view of statistics, it does matter. Statistical consideration, you might say. It matters in the components of this. So each of these, let's say theta 1, will look like this. Theta, the first component will be theta 1, 1, up to theta 1, p. And theta 2 would be theta 1, 2, up to theta 2p. The components here are completely different. Now, both of these lead to the same predictions. So does it matter? Well, from that point of view, no. If somebody comes to you and says, well, predict for me the output for this X, you can give the prediction with either this or any of these others. So that's not an issue. But what if they then say, well, what is the variable that influences the output most influences the output? Which of these thetas? Well, you've got a whole infinite number possibly of these, and you don't know the answer to that. So this is what we call an identifiability problem. And we can sum this up in plain English as saying that the model lacks explainability or interpretability. So this is a problem. If you run a trial and you have lots of data and you want to determine the influence of lots of predictors or features or inputs on an outcome, you need to know which of the features or inputs are influencing the outcome the most. Because based on that, you need to make decisions, real decisions that have consequences, right? So this is a safety critical matter. You can't just willy-nilly hand out treatments and drugs and perform operations or whatever procedures. You have to know why. And in order to know why, you know what's influencing the outcome. Right? But if someone comes to you and says, well, we can predict if this person is going to have this problem or not, but we can't tell you why, right? We can't tell you what is the most crucial factor in this or what are the most crucial factors. Well, that's not good enough, right? So in many cases, this identifiability problem or lack of interpretability is a problem. So OLS in those cases can be problematic. So what does regularization do? So this is another view of regularization in these cases, or another use of regularization and why it's so potentially useful is that it selects a particular solution. So in the case of Ridge, it will select a unique solution. By introducing a penalty, you turn what was a problem that did not have a unique solution into one which does have a unique solution. Lasso may not have a unique solution, but it favors sparse solutions. So it will select certain features and it will say those are the features that are most important because it will set many of them to zero or very near zero. Okay, so with all that aside, because the reason I'm going through this is, first of all, it's important that we understand this. And secondly, because in this example, we are going to set p greater than n. We're going to set p equals 60. We're going to have 60 features and only 40 data points. And I'm doing this deliberately so that we could see what Lasso and Elastic Net do in this case. And it also showcases the power of Lasso, this selection property. That even though there are 60 features, Lasso in the end will only select a very small number of them. Right? And it will say, these are the features that matter the most. Now, ideally, what we wanted to do is select only the first one. So we will see whether or not it's capable of doing that. So we're going to, in this example, on purpose, select p greater than n. So we're going to have 60 features and 40 data points. And the inputs are going to be selected randomly. So we can select them anywhere we want. The first one we could select according to some regular grid. We could choose values of the first feature x1, some regular set of values like 0.1, 0.2, etc. But it doesn't really matter. We could just select them randomly. So we're going to select x1 and all of the features except the second one randomly. So randomly according to a standard normal. So this is a normal distribution with a mean of 0 and a standard deviation or variance of 1. So all of them except the second one are going to be selected like this. So once we've selected these, and we mustn't confuse the subscript j here with the data points, the subscript I for data points. So what we have is a random sample in which we have the ith random vector. So the general case, we have x equals x1 up to xp, right? And we have a random sample. We have I equals 1 up to n of these. So what I'm going to do is I'm going to label them like this: xi1 to xip. Right? So xi, let me write that out again because you can't clearly see it. xi1 up to xip. Right? So here where I'm referring to the individual coordinates of these vectors. And so the first one and the third one up to the pth one are selected like this. Now, once we've selected these coordinates, what we're going to do is generate, as I explained earlier, the yi's. So the outputs yi are going to be equal to x I1, only the first feature, plus some random noise. We call that epsilon I. So this is how we're going to generate our data, our synthetic data. The rest of them have no influence on yi. We didn't include them at all in this data generation. Now, the second feature, we're going to make that correlated with the first feature by setting x2 to be equal to x1 plus some noise, which I'm calling now eta, so we don't confuse it with the noise that we add to x1 to generate y. And this eta is also normally distributed with a mean of 0, and I'm going to give it some variance sigma squared core. The core here indicating that x2 is correlated with x1. So let's have a look at the results. So let's start out first with a standard deviation for our noise epsilon. So remember, epsilon here appears in y equals x1, first feature plus epsilon. And that epsilon is distributed according to a normal with a mean of 0 and some variance sigma squared. So the standard deviation sigma here I'm setting to 0.5. And what we're going to do is select the hyperparameters. So what are the hyperparameters here? Well, in Ridge, we solve this problem. We solve a penalized empirical risk problem. Let's just write it as a half the error rather than the empirical risk. Phi theta minus y squared is the 2 norm plus lambda over 2 norm of theta squared, right? And that's the 2 norm. And in Lasso, what we do is we replace this with plus lambda norm of theta, but the 1 norm. So that's Lasso. So this is Ridge. This is Lasso. We solve this plus this. And in Elastic Net, what we do is we combine these two. So we solve this plus, now let me write it this way, lambda, so we're only going to use one lambda rather than, we can use two lambdas or we can just use one lambda. Lambda times, let me call this t, norm of theta, the 2 norm squared, so we've got here another parameter t, plus lambda, the same lambda times 1 minus t times the 1 norm of theta. So what we have here is a mixing ratio. So this t is any number between 0 and 1. If we set t equals 0, we have pure lasso. If we set t equals 1, this becomes 0 and we have pure ridge. And anything in the middle will be a mix of lasso and ridge. So this is typical way of doing it, rather than having lambda, calling this lambda 1 and this here lambda 2. We solve it like this. So this is the way I'm doing it. Now, these lambdas that I just wrote down are selected using a grid search cross validation. So CV here stands for cross validation. And we combine this with what's called a grid search to find the optimal values of the lambda. This is something I haven't discussed so far. I've been talking about these lambdas, but I never actually said how we select them. Now, I'm showing you this first, this example, in which we use this to select the lambda before I explain to you what it actually is, because it seems a natural way to do it, because we've finished with Elastic Net and Lasso. So I want to show you some examples. It's the right moment to show you some examples. But at the same time, I don't want to drown you in the reasons why, because they're quite technical, and it's going to take us some time to understand why we do cross-validation and how that's combined with a grid search in order to tune or find the best values of these hyperparameters. Because we have to discuss model selection, selection bias, and various other things. And so I need to explain that to you properly. So for the time being, just see this and this fivefold. This is an example of k-fold cross-validation combined with the grid search as a way to select the hyperparameters. And immediately after this example, we're going to go into this, what this means, and general subsampling or resampling methods. So we're going to select the hyperparameters, to summarize, using this procedure, which I will explain after this example. And I'm going to reserve 30% of the data for testing. So what do I mean by that? Well, we have 40 data points, right? N equals 40. So I'm going to reserve a third of that, or not a third, but this times 0.3, whatever that is as an integer. I'm going to reserve that many points for testing. That means once we've trained our algorithm, once we've first found the best value of lambda and trained our algorithm and got the theta for ridge, for lasso and elastic net. So we're going to get theta ridge, we're going to get theta lasso, and we're going to get theta elastic net. Once we've done that, using only 70% of this data, we are then going to test. We're going to look at the error, the generalization error. This is a true measure of the error on this 30% that we reserved of the total data for testing. So we call this test error or generalization error. I've discussed it earlier. Okay, so what happens? Well, now let's have a look at the results. So along here, we've got the feature index. So along here, we're looking at theta j, and this feature index is this j here. So these are the values along here. This is the value, the coefficient value, coefficient meaning theta j, with each of these ridge, lasso, and elastic net solutions. These are their values. Right, so the value is indicated along this axis here, and this is the index from j equals 1 up to 60. There are 60 of them. Right? Remember, we had 60 predictors xi, and so we had, let me call that j. So we had 60 of these corresponding coefficients. So what does Ridge do? Well, the optimal value of lambda we found for Ridge was 1 using our fivefold grid search cross-validation. And so Ridge is given by these blue lines here. These are the values. So theta 1 is about 0.3. Theta 2, what is theta 2? Can't really see it there very clearly. There'll be some value there. Theta 3 is 0.3 and so on. Some of these values are negative. And you can see that Ridge distributes these values fairly evenly across J. So none of the, not all, certainly, and many of them are far from zero. You can see all of these large spikes here, whether they're negative or positive, are not close to zero. Some of them are, like these values here. Some of these are close to zero, especially this one here, and some more here, like this one. Some of these are close to zero, but most of them are not, it appears. So we can say that the values of theta are distributed across J. What about Lasso? Lasso sets most of them to virtually zero. There are a few notable ones. I mean, this one is pretty small. It's more or less almost zero. This one is notable, and so is this, and there are a few more here. But it's selected essentially the first one. Right, this is the first value. This is theta 1, and this is theta 1 as well. It selected the first value. It said basically that theta 1 is not about 0.8, right? And theta 2 is basically set to 0 correctly, because theta 2 is basically just theta 1. They're highly correlated. And the rest pretty much are 0, the random features, which should, if the solution is correct, all be 0. Now, they're not exactly 0, but most of them are virtually 0. And there are a few exceptions which are close to 0, but not quite 0. Perhaps not as close to 0 as we would like. But we have to remember that we've injected a fair bit of noise into the data. So our yi's are xi, the vectors xi, plus epsilon I. This epsilon I, we've injected a fair bit of noise because it has quite a large standard deviation. Right? So this is why we have this. Right? They're not all quite 0. But certainly we do get a good degree of selection. It set most of them to 0. Now, what about Elastic Net? Well, Elastic Net is somewhere intermediate between Lasso and Ridge. So Elastic Net also gives us sparsity, but not quite as much sparsity as Lasso. But it still does very well. And if we look at the mean square error on our test set, so Lasso, the optimal lambda we got is 0.1, and in Elastic Net, the optimal lambda was also 0.1, and that ratio, the t, or 1 minus t in this case, was 0.9. So 1 minus t is 0.9, t is 0.1. So basically, it only selects 10% in this mix t norm of theta 2 norm squared plus 1 minus t, the 1 norm of theta, 1 minus t times this. T is 0.1. So this is 0.1 and this is 0.9. So it favors Lasso, right? It correctly favors Lasso. Now, if we look at the mean square errors, you can see here that Ridge has a much higher, 3 times higher mean square error than Lasso and Elastic Net. So both of those are comparable. Ridge is clearly less accurate. Okay, so that's the one example. Let's now lower the noise or standard deviation of our noise epsilon to 0.25. We're going to halve it. And here you see now Lasso more aggressively because there's less noise in the data. The data is cleaner. We see an improvement in both Elastic Net and Lasso. So Lasso really is very sparse. It very aggressively only selects the first feature X1 correctly. And now with a value of around about 0.85. And the rest are virtually zero. And the same with Elastic Net, although Elastic Net uh, does seem to select the first and the third feature. So the first feature, it gives a value of about 0.6, and the third feature, or is that the second feature? No, actually, I think that's the second feature. It gives a value of about 0.3. So that's not quite correct. But nevertheless, if we look at the MSE, both Elastic Net and Lasso are far superior to Ridge. So we still get the sparsity with Elastic Net, but it's not as aggressive as it is with Lasso. Lasso really does aggressively only pick here the first predictor X1 correctly. So here you can see really the advantage of Lasso when it comes to these sorts of problems where we have collinearity or multi-collinearity. So multi-collinearity is the same principle. I should have mentioned this earlier. So in collinearity, we have something like theta. The ith one is highly correlated with, say, the jth one. Right? Might look something like this with some small noise. But we could also have cases like this. So let's say Cj plus Ck theta k. So theta I could be a combination of the jth and the kth one. So this we would call multi-collinearity. Right? It's the same principle. So Lasso really does, in this case, where we've designed our example such that we have this collinearity, we've got this theta 1 or x, why am I using thetas here? X, j, in our case, that should be an x. In our case, we have x1 or x2 is basically x1 plus a little bit of noise, right? So we have collinearity. What I'm saying is that we could also have had x2 is x1, x1, x2 is x1 plus x3 or something like that. In that case, we would have called that multi-collinearity. Okay, let me clear that mess. So that's the advantage of Lasso. And let me show you one last example here. So what happens if we set P equals 5? So we have only 5 predictors now. So rather than 60, we use only 5. Well, here we're going to have n is greater than p because n is 40 and p is only 5. So here we don't have that problem of identifiability, right? But what is that? But we still have the collinearity of x2 and x1. Now here the mean square errors are similar between Ridge, Lasso, and Elastic Net. There's almost no difference between them. Right? And here the optimal Ridge lambda is 10, the optimal Lasso one is 0.1, the same with Elastic Net, and the ratio is optimal one is still 0.9. So in Elastic Net, I should have said, we are actually optimizing over the lambda and this ratio t at the same time. So there are two hyperparameters there. Or equivalently, we could do lambda 1 and lambda 2. Doesn't really matter. So the mean square errors are similar, but what Lasso does is correctly identify that most of the weight, at least anyway, should be placed on the first predictor. And it eliminates the second predictor from consideration. Right? So Lasso has interpretability here, whereas Ridge doesn't, because Ridge is actually giving roughly equal weight to x1 and x2 incorrectly, because x2 is actually the same thing as x1. And it also gives weight, quite a lot of weight, to some of the other features as well. So in this case, while the mean square errors are similar, Lasso still has interpretability, identifiability, and interpretability. Elastic Net is somewhere in the middle, although it also does pretty well. These values are quite small. This one is negligible. These two are virtually negligible. We could pretty much set those equal to 0. Okay, so that takes us to the end of this example. Now, the code for this, I should have mentioned this at the beginning, is in the description to this video. And what we're going to do next is we're going to look at this cross-validation and grid search, because we need systematic ways of selecting hyperparameters. So there are several things we need to understand before we get to that point. We need to understand what a hyperparameter is. I need to define this. And then we need to understand how we select those values. But in order to understand that, we need to know what the issues are involved in selecting these values.